working on your Kirchhoff's laws problems. What I did was I'll show you what I did. I created a octave program so that all I had to do was put in your resistor values, and then I could check your results instead of having to go. So the way it worked was, let me find the file. And let's see there. I don't know what happened there. How do I go back? Here we go. We're going to stop a few minutes early today. There's an interview for a position that I'm on the committee, so I want to make sure I have time to get there. So it wasn't a very long program. So I input the 5 resistors. I create a matrix associated with the 3 junctions and the 3 loops, and I put in the B matrix associated with the 6 equations. Then I did the inverse of A times B. That was the answer. And then to find the current, you had to multiply the voltages by the current to find the voltages. So that actually should be V, but it doesn't really matter. You had to make sure you multiplied the correct currents by the correct voltages. It wasn't like you took I1 times R1 and I times R2. It was each current had, you can notice here, I1 had R1, I2 had R3, I3 had R2, I4 had R6, I5 had R4, and I6 had R5. So if you use those incorrectly, then you've got the wrong answer. So there were 2 people that got it right, so that was the hard part, because I've made the program. Okay, I'm going to test the program. I'm going to try using the people that I think usually get them right, and they didn't get it. They didn't match my answer, and so I'm like, okay, did I write the program wrong, or did they do something wrong? And so I double-checked everything, and finally got a student that agreed with me. It was Savannah. So she gave me hope that I was doing it right. I was like, oh, all right. What's that? No, you're still right. Yeah, you were right. So you were one of the 2 people that got right. The other one was Seth. Everybody else got something wrong. So then I had to go look through all those equations. It gave me a headache. Most of the time it was things like there were sign errors. One little sign error throws the whole thing off. Maya's was funny though, because you made one sign error. Okay, but when you used the right numbers, you actually got 0 current through like 2 of the. Yeah, no, I've never had that happen before. Your answer didn't have a 0, so you got. But if you had done it correctly, you would have gotten 0 current. So that particular combination of resistors that you had actually ended up with two of the loops, not loops, but 2 of the parts of the circuit having 0 current. Just worked out that way. So what am I going to do? I'm probably going to give them back to you, and you're going to find your errors, because I want you to understand where you made a mistake. And if it was just a sign error, I usually showed you where the sign error was, and I want you to go back and fix it and redo the matrix. Some of the other ones were a little bit more of an error, and at that point you may just need to come and talk to me, and I may need to explain to you or find somebody. I was thinking of giving the people who knew what they were doing extra credit by helping the people who didn't know what they were doing. So, what do you think about that, Savannah? You like the extra credits. You don't like the idea of putting you under pressure. So, anyway, So we're going to finish up chapter 14. We were talking about sound intensity. And the sound intensity is the power, the energy, well, the power in the sound wave per unit area. So I'm just going to work a simple example here. So let's say you have some sound source. Hold on. I don't know why I usually turn this off, and sometimes it comes back on even though it shows it being off. I don't understand. But anyway. So let's say we have a 70 watt sound source, like a speaker. It's kind of like a three-dimensional Alexa. You know, it's like a ball, so the sound goes out in all directions equally. So the question is, what is the sound intensity at 10 meters? So all you have to do is, you can see the sound intensity is just equal to the power, the average power, and because we're assuming it goes out spherically, that's 70 watts, and you divide by 4 pi r squared. So the radius of the sphere is 10 meters. So we just plug the numbers in. So you get 70 watts divided by 4 pi r squared. 4 pi r squared is the surface area of a sphere. So you get 4 pi times 10 meters, quantity squared. Get my calculator. Uh-oh, how'd that happen? Okay. I even checked it on my calculator to see, doing my matrix inversion, and agreed with what I had. So you guys all messed me up because I didn't have faith in my ability. But actually, I was doing okay. It was you guys that were messing up. Too many of you. Okay, so the sound intensity at this particular point is 0.0557 watts per meter squared. Now, what is the next question is, what is the sound intensity level in decibels? Question mark. So decibels is equal to 10 times log to the base 10 of the intensity divided by this reference intensity, which is 1 times 10 to the minus 12 watts per meter squared. So we just have to plug it in there. So you get 10 log base 10 of 0.0552 divided by 1 times 10 to the minus 12. These are both watts per meter squared, which has to be because you can't have units when you take the log of something. So we take 10 times log of 0.0552 divided by 1 e to the minus 12 power, and we get 107.4 decibels, which is reasonably loud. I don't think it would damage your hearing, but your grandparents may say, it's too loud. So, if you move away from a sound, the sound gets a lower intensity. So let's say instead of at 10 meters, the next question is, what is the sound intensity for this particular scenario, what is sound intensity at 100 meters? So the relationship, because the the formula for intensity is power divided by 4 pi r squared. If you're looking at the sound between 2 points, and what we know is we know the sound at 10 meters is equal to, we don't use decibels, you have to use watts per meter squared is 0.0057. So that's 0.0557 watts per meter squared. And that, let's call that R, 10 meters is 10 meters. So the question is, what is the intensity at 100 meters? So the sound intensity at 100 meters is going to be equal to the sound intensity at 10 meters times the ratio of the radiuses, but it's going to get smaller, so we want to have the smaller number on the numerator. So it's going to be R at 10 squared divided by R at 100 squared. So we get 0.557 watts per meter squared times 10 squared, 10 meters squared, divided by 100 meters squared. So let's see what we get. 0.0557 times 100, or 10 squared, divided by 100 squared. And so you get 5.57 times 10 to the minus 4 watts per meter squared. It makes sense because you have the distance is 1/10, but the sound intensity is well, not 1/10, yeah, 1/10. So when you square that, you get 100th. So this number is 100th of the previous number. And is that 2 or 7? I don't know. Maybe I wrote that wrong. Is it 7? Okay, I don't know why I wrote 2 over there. Okay, so anyway, now let's see what the decibels associated with that are. So the decibels at 100 meters is 100 log base 10 of 5.57 times 10 to the minus 4 watts per meter squared divided by 1 times 10 to the minus 12th watts per meter squared. So we take that, divide by 1 times 10 to the minus 12th, take the log of that, times 10, and now the sound level is 87.5 decibels. It's probably, actually, I probably used the wrong number here. I think I used 2 there instead of 7. Because they should be 20 decibels apart. This should be 5. So obviously, getting away from your sound source is going to reduce it. And from a decimal standpoint, 10 decibels we perceive as twice as loud. So here we have a 20 decibel difference between these two conditions. So this is going to sound 4 times, so this will sound 4 times as loud as that. So moving from 10 meters to 100 meters makes it so the sound perceived by us to be 1/4 the amount, the 1/4 the sound level. Okay, so that's how sound or distance affects sound level and perception. The next thing is, what if you have 2 sound sources at the same point, and say you have 2 trumpet players instead of 1 trumpet player? Do 2 trumpet players sound twice as loud as 1 trumpet player? You might think that's true, but it's not true. Okay, so let's look at it. So let's say we have, so we'll say, okay, so we have 1 trumpet player whose decibel level is, and this is at a given radius. So we're just saying, so there's a trumpet player out there playing something, I'm a certain distance away, and I'm perceiving, let's say, 80 decibels. What is the decibel level of two trumpet players? So they're sitting next to each other. Oh, by the way, I read this article about music. So there's this guy who's playing in a orchestra in England, in Liverpool, and they don't have to play just Beatles music because it's Liverpool. So they were playing some Wagner, some Wagner opera, and so they're in this orchestra pit, and this guy plays the violin, and behind him is the horn section. There's like 10 people in the horn section. And this guy has suffered permanent disability because of the loudness of the horn players playing right in his ear for a certain number of time. He lost hearing and he has mental problems and all kinds of stuff. Let's see if I can find the article. I think it was on the BBC. I'm not sure what I would look up. What would that be? Maybe health. I'm just looking in the articles here. Man's has world's worst super gonorrhea. That's one article there. Buying Viagra, what you should know. Okay. That's apparently not going to. What's that?
I think I found it.
Oh, did you?
Yeah, but it's the Washington Post.
Oh, is it Washington Post? Oh, yeah, that's one of my. So what does it say?
Basically, the title just says the orchestra's horns were so loud they wrecked the violist's career
Yeah.
and his hearing.
Yeah. I don't know if there's a search on this thing. Anyway, yeah. So that was kind of interesting. So trumpets can be loud. So what we're going to do is we're going to find the sound intensity associated with decibels, because we don't add 80. The answer is not 160 decibels, obviously, because a jet engine is like 140 decibels. So two trumpet players aren't that bad. So what you would do is you would convert, you would take the expression for decibels, which is 10 log base 10 of I divided by I0, and solve for I. So let's do that. So you take decibels divided by 10 is log base 10 of I over I0. And then you would raise both sides to the 10th power. So you'd have 10 to the decibels over 10 is equal to 10 log base 10 of I over I0. But because these are inverse functions, it just becomes I over I0. So the sound intensity is equal to, sorry, not I0, but the sound intensity level in watts per meter squared is equal to I0 times 10 raised to the decibels divided by 10. Okay, so let's plug that in there. 1 times 10 to the minus 12 watts per meter squared times 10. Number of decibels is 80. Divided by 10, so it's 10 to the 8th power. So you get 1 times 10 to the minus 12 watts per meter squared, 10 to the 8th power, which is equal to 1 times 10 to the minus 4. How did I know that? Because I've got 10 to the 8th times 10 to the minus 12th. They have the same base, so you add the exponents. And so negative 12 plus 8 is negative 4. Okay, so that's the intensity of one trumpet player. So to find the intensity of two trumpet players is you just add the two numbers. So two players playing the same, two players at 80 decibels is going to be 2 times 1 times 10 to the minus 4th watts per meter squared, which is 2 times 10 to the minus 4 watts per meter squared. So now we go back to decibels. So we're going to convert back to decibels. So decibels is 10 log base 10 of I over I0. So we just have to plug in the numbers now. 10 log base 10. I is 1 times 10 to the minus 4 divided by, 2, sorry, 2, because I got 2 trumpet players. 2 times 10 to the minus 4 divided by 1 times 10 to the minus 12. These are both watts per meter squared. And it's going to be somewhere greater than 80 but less than 90. So you get 10 times log base 10 of 2e to the minus 4 divided by 1 e to the minus 12, and you get 83 decibels. So 2 trumpet players don't sound twice as loud as 1 trumpet player. They sound... So the other question is, how many trumpet players do you need to get twice the amount of sound? And it's probably like 3 or 4, okay? I'm thinking. I'm not exactly sure. What you would need to do is to go up to the next level. So if each one is one, maybe you'd have to have 10, right? You have to have 10 trumpet players to sound twice as loud as 1 trumpet player. That seems kind of weird, doesn't it? Go ahead.
So why is this? Is it because of how the decibel scale is, or is it actually like perceived intensity?
It's both, okay? Because the decibel scale turns out that, and I don't know if it was, I don't think they chose it that way, but that's just the way it turned out. I don't think it was any kind of scientific principle. It just turns out that 10 decibels is about twice as loud as far as our perception of sound, how our brain works.
In the book, it said it's approximately logarithmic. I think they just found a graph that
Yeah,
fits it.
they probably asked somebody, tell me when, is this number twice as loud as the next one? They could say, and then they probably did some experiments, said, oh yeah, it's so. And that, one thing that I've always thought about is, when you play in a band and you have a soloist, why, you've got a band of 50 people and you have the oboe, even though the oboe stands out for other reasons besides just, but, how do you hear a soloist if it's only 1/50th of the band? Then why do you even hear what they're doing? You might have, one, there's the reason the band doesn't usually play as loud during that period of time, but also I think it's related to this, the different instruments, all those other ones added together don't make 50 times the sound they make, so you can still perceive that or the soloist singing, one person singing versus a choir singing, you can still hear the one person singing when you cut everybody out. And I guess part of it is just the hearing. Usually I put something like this on the test, where you have to take a decibel value, convert it to a sound intensity level, and then multiply it by however many. It may be asking you what the decibel level of twice the number of contributors to the sound, or maybe asking to double the level or to increase it from 80 decibels to 85 decibels, how many people have to be playing to make that happen. When I have the review, you'll see I'll talk about that as well. So here's a band question for you guys. So do you ever get home and you're like, hopefully you do practice at home a little bit, right? Okay, you better. You're going to music. You're a music major. The rest of you maybe don't have an excuse, but there's a piece that you don't understand. You're not sure about. So you play it, and then you play it again. You play it again. Play it again. So I was doing that last night because there's this piece called it's from Toy Story. I think I was telling you about that. Let me see what the name is. You've Got a Friend in Me. Anybody recognize that? Yeah. Okay, so we're playing that, and I'll just you probably can hear this even though it's from my phone. Now that's not a band, that's some kind of MIDI recording. Now I'm playing this part. Ba-da-da. So it's a counter melody kind of. I guess, would you call it a counter melody? I don't know. It's not really a melody. I don't know. So we were practicing it on Wednesday night. For one thing, I mean, I recognize the song. I'm not Toy Story aficionado or anything like that. So I'm like, oh yeah, I've heard that song before. I know the melody. But when you're playing something like you and me, second trumpet and that, you're playing something that's not the melody. So if you get lost and try to figure out where you are, how do you know? You just don't know. You have no idea where you're listening to them playing the melody. And so I told him on Wednesday night, I said, this is hopeless. There's no way I'm going to do this. And we only went through it twice. I mean, it's like twice. I'm sight reading the first time, and then the second time, it was like I was begging him to do, can we do it one more time? I'm trying to learn this thing. And so I was looking for a recording, and this recording is not our arrangement. So originally I was thinking there's no way that I can use this arrangement to help me, but it turns out that some other part has enough of my part that I could actually pick it out. So I listened to it, I guess the other day. I listened to it just to see what it sounded like, and I convinced myself that I couldn't use it, but I was getting desperate because everybody else seemed to get it. Either they'd played it before, or their trombone's playing the melody, and I'm like, yes, finally the melody. So it was an interest. I spent about 45 minutes playing this song over and over and over and over again. And I finally was getting pretty comfortable with it. When I first started out, it was pretty pathetic. But I wouldn't say I'm ready, but I'll be ready by next Wednesday. I was going to email everybody and say, hey, I'm ready. Don't cancel this music, because I like the song. It's a fun song. But when you're not playing the melody, you don't know the song that well, and you get lost. Now, somebody who's in the band told me that their band director said, if you get lost, don't put your instrument down. Is that a true statement? Pretend like you know what you're doing? Yeah, because usually when I'm lost, I just put my instrument down, and I'm very obvious about it. I mean, it doesn't make any difference as far as the sound is concerned, but I guess other people don't know that you don't know what you're doing. So, oh, they're resting. Yeah. Well, I guess I could say that. I was resting. Okay. Let me see if there's anything we haven't talked about sound. Doppler effect. Interference of sound waves, to talk about that. Standing waves, talked about that. Oh, I know. Yeah. So Steve Metzler was there the other day, and we were talking after class about why Seth's group measured the sound intensity in the tube. And for the fundamental frequency, they were getting the highest intensity in the middle of the tube, and I had told you that there was an antinode, not an antinode, there was a node in the middle of the tube. And I was thinking, why is that wrong? And yeah, Steve was a physics major, but I don't think he learned it from physics, because I went back to the book and read it, and it wasn't very obvious from the book either, so it wasn't something I missed. So I was going to explain why that was the case for the open tube open at both ends. So let me describe this. So here we have the tube open at both ends. This is our typical musical instrument in simplified form. And what I said was that what I showed was this kind of a graph of intensity versus position. And I showed something kind of looked like this. So it came down, went through the middle, and then went over there. And so then the wave, I was saying the intensity was something like that. So this was a node, and these were antinodes. But when we took the microphone and we stuck it down that thing here, so here's the microphone, and if I plotted sound intensity as a function of position, so here's my sound intensity as a function of position, what I found was something like this. So we got the highest sound intensity in the middle, but according to what I was telling you, I was thinking we should get the lowest sound intensity in the middle of the tube. Okay, so as we moved it, it got greater right here. So here's the explanation. There is a displacement antinode, or node, sorry, in the middle. This is for the fundamental frequency. But what we were measuring was the pressure. So there is a pressure node, antinode, sorry. Keep these things messed up. So what does that mean? Because what I was showing you here, what the graph I was showing you, and the one you see in the book, is a displacement. And that's because if you think about the air, the waves that are traveling through here, because this is a standing wave, the middle, because it's right in the middle of the tube, can't go either way. It's going to, the actual air molecules right in the middle don't move. But what happens is they get smushed together and they get spread apart symmetrically. So when you look at the pressure, you get a high pressure and a low pressure, a high pressure and a low pressure. But the actual molecules, the molecules don't move in the middle. So that's why we were seeing the behavior, because the thing I was telling you about was a displacement comment, whereas we were measuring pressure. What's happening on the edge of the tube? And in reality, doesn't actually. You would say there's a displacement antinode. So the molecules are moving back and forth like this, but they're the same distance apart as they move. So even though there's a wave traveling through here, the actual molecules at this point they're not changing in compression. So the actual end of the tube varies a little bit. Okay. So it's not ideal. But so the pressure's not varying here, but the displacement is the maximum. Here, the displacement is 0 because it's symmetric, but the pressure fluctuation is the most. And then on the other end of the tube, you have the displacement's maximum, but because the waves, the molecules aren't getting closer or further apart, then there's no pressure. So that's the explanation. So that's pretty cool. Now, if you have a tube closed at one end, so we'll draw another tube with some way of showing that it's not open. So we'll tell you which end's closed. So this is the closed end. So because from a displacement standpoint, it can't move because there's a solid wall. So this is going to be a displacement node because it's a solid surface, but these molecules are going to be moving back and forth, and so it's going to be a pressure. It'll be a pressure antinode, but a displacement node. Okay. all you have to do is figure out, based on the dimensions of the tube, the speed of sound, and what else? That's about it. You can figure out what the harmonics are associated with it. So, and let's see what we got here. Yeah, I was going to show you I found a video or a demonstration that kind of explains what I'm just talking about. Let's see if I can find it. Tube open at one end. There we go. And this just gives me a link. So it goes to show you, sometimes when reality doesn't agree with theory, it's most likely you just have the theory wrong. I mean, reality is a reality, right? So you can't change a reality. So somebody asked this question, and this person gave an answer, and they have this nice little diagram. So this is a tube closed at one end. So you can see how these particles don't move, but they're getting smushed. So this is going to be a displacement node, but a pressure antinode. This is actually the displacement. So you get the maximum displacement right here. You can see how they're moving a lot, but they're not. The distance between the molecules is not changing that much. Then we have a node here. So we have a node here and a node there. This is actually the second harmonic, I think. So again, at this point, you've got this symmetric nature. So these points are not moving. So it's a displacement node, but you can see how they're compressing it, high pressure, low pressure, high pressure, okay? So they're always opposite. Where you have a displacement node, you have a pressure antinode, and where you have the other way around. Now over here, at the end of the tube, we're saying we have a displacement antinode, because these things are moving the most in displacement. But if you look at the distance between the particles as they pass through this plane, they're the same distance apart, and therefore there's no pressure associated, no pressure wave associated with it. Okay. So I like that little demonstration. Now, the complicated part is interesting. They were saying that the reality is that you've got this governing differential equation, which says the second derivative of the pressure with respect to, this is the one-dimensional acoustic pressure wave equation. Second partial derivative pressure with respect to x is equal to 1 over the speed of sound squared times the second partial derivative of pressure with respect to time. And if you solve that differential equation, you get something that would describe that behavior. But they were saying in reality that you actually have a much more complicated expression. That's just to show it's complicated. Okay, so we can close that. Okay, got tubes and also this stuff. We talked about the beat frequency. I wonder if this, let me check this link out, see if it works or not. Oh, no. And that talks about the different kinds of instruments. So here's a flute. We looked at a flute, actually looked a lot simpler than that. What they're showing there is that the second harmonic has the most energy, and it's showing the resulting waveform. So this has various components, and so it's a periodic function. The pressure as a function of time is periodic, but it's not a simple harmonic function, and that's because you're adding all these different harmonics together. So this was from the book For clarinet, it says the fifth harmonic is very strong, and first and fourth harmonics are similar. For the flute, the fourth harmonic is close to the strength of the first harmonic, and the second harmonic is very strong. So they're basically looking at a fast Fourier transform. And I think that's about it. Okay, so I already said I assigned homework for chapter 14. So that's it for chapter 14. We're moving on. We've already done chapter 15. So the question is, do we go back or do we go forward? And normally I go back, but this year I'm going forward. So if I went back, we talk about heat transfer and thermodynamics and temperature, which if we have time at the end, we will. But I want to make sure we talk about going the other direction, which is chapter 22, I think. Yes. So chapter 22. So we're going to talk about we're still talking about waves, but we're talking about waves for light waves. So we started off with talking about electromagnetic waves. We haven't talked in detail about them. We went back and just talked about waves on a string, about oscillating motion, and then we talked about sound, which is sound waves and what kind of things happen. And the same kind of things can happen for light waves. But the next two chapters talk about ultimately how optical instruments work, how mirrors work, why your image looks like it does in a normal mirror. If you have a curved mirror, why does it look different? How do glasses work? How do telescopes work? How do microscopes work? So chapter 22 is reasonably short, and we're going to talk about some basic concepts of light. So the basic things that happen with light are reflection and refraction. So you don't write all this stuff down. So here's the brief history of light, which of course light wasn't discovered in 1000 AD. It's always been around from the beginning. Okay, so originally it was proposed that light consisted of tiny particles. And that was what Newton's concept of light was. So you can think of it little balls. And so when something reflects off a surface, it's like taking a ball, throwing it at an angle. It's going to bounce off at an angle that you can kind of predict. It's like playing pool. If you hit a ball to the bumper and it comes in at a certain angle relative to the side, it's going to bounce off the same angle relative to the side, but in the direction that you're hitting the ball. And you can use that theory to explain reflection and refraction. But then this guy Huygens thought maybe light was a wave, because there are other things that you can't explain from the principles using it as a particle, like light bending around a corner. It's not very big, but it does actually happen. So there are phenomenon that you can't explain as a particle, but there are also things you can't explain as a wave. So ultimately what happened is, in our current understanding, is that light behaves both as a particle and a wave. For reflection or refraction, it's mostly like a particle. Okay, so here's more. In 1801, this guy Young did this experiment. So let me explain this experiment to you. He also thought you can explain this using the behavior of light as a wave. So he took a source of light, and then he made these really small slits in a screen. And then he had a projection screen. So there's a light source that's coming in here, and these are really small slits. And what you would expect, if you think it is a particle, you just end up with light maybe here and light there on the the projection. So this is dark, so you get light coming in. But what happens is you actually see the intensity of light looks something like, if I draw it, it kind of looks like this. So there's actually some light in the middle where you wouldn't expect there to be, and then it kind of goes like this. And if you take water waves and you take the water waves against this barrier, what will happen is the waves will go out like this, and you'll get what this is called an interference pattern. And you can also do this with sound, where the peaks of this wave constructively interfere with the peaks of this wave to give you a peak here, and then other places you get destructive interference where the peak of this wave goes with the trough of this wave, and you get them canceling out. And so they saw this behavior that they saw from other things that behave as waves, and they said, well, light must be a wave. So there was another thing. And then Maxwell came along and predicted that, oh, these light waves actually are electromagnetic waves. So that was another feather in the cap for the wave guys. Then Einstein came along and he observed something called the photoelectric effect. And the photoelectric effect could not be explained through waves, treating light as waves, but it could be explained as being particles or fixed quanta. It'd have fixed energy levels. But ultimately, and this guy, Max Planck, used Einstein's ideas to explain why certain elements emit or absorb certain wavelengths. And that comes down to the fact that light, visible light, is caused by the electrons moving from one energy level to another, and as they move from one energy level to another, there's a fixed amount of energy that they either absorb or emit, and those fixed energy levels are associated with a fixed frequency. And they came up with an equation to predict that. What is the energy associated with the frequency of light? And that helped explain the photoelectric effect. So that kind of was like a particle. Anyway, so that's my brief history of light. So first particles, then waves, then some more particles. Now it's both. Duality of light. But to explain things like mirrors and lenses, you can just use a form of particles. You can also explain a lot of it using waves, but it's easier to explain using particles. So let's talk about, so what is ray optics? So what does it explain? It explains reflection and refraction. And what you do is you treat light. So let's say we have some kind of object and from this object you have light that is transmitted, and we're basically saying that the light travels in a straight line. So if we're looking at, so assume this is my calculator, and what's happening is the light from the projector is going here. That light is then being absorbed by the electrons, and it's shifting them to a different energy level. But then that's not stable, so then it goes back to the original energy level, and it transmits. It then sends out energy. So the energy from light comes in here, and then the energy from this goes out at certain wavelengths, and our eyes see it and perceive it as such. But the energy that's coming out of this surface is going off in all different directions. But it's going off in all different directions in a straight line. So we treat them as rays. So this point on my calculator is going out like that. And if I look at this point down here, this also is having light rays go off in all different directions. And then what we perceive, here's our eye. Okay. So we are capturing this ray of light from this point. This ray of light we don't see because it's going somewhere else. So we're only collecting certain rays from each one of those points, and we take all those different rays and process it through our eye to perceive sight. So that's what we mean by ray optics. We're going to be drawing a lot of lines with arrows on them. Also, remember back in chapter 21, we had this relationship that said the speed of light is equal to the wavelength times the frequency. We can also say that the speed of light in a vacuum is approximately 3.0 times 10 to the 8th meters per second. What is the speed of light in glass? Is it the same? Does the speed of light change when you go through something other than a vacuum? So going through space, it's always the same speed. But now it goes through my glasses, say. I'm looking up at the sky. Actually, it's already been through the atmosphere, but let's assume that it's... So it turns out that if you go through anything other than a vacuum, the speed of light is less. And depending upon the material that you have, and it has to be, of course, transparent to get through it, so it has to be transparent, but of different transparent materials. So the answer is it's slower. I'm not going to tell you how slower yet. So when you say I can't go faster than the speed of light, you can't go faster than the speed of light in a vacuum. The speed of light in my glasses is lower than the speed of light. So the speed of light in my glasses, I guess it can't go any higher than what it is, but it can go higher by taking that light from my glasses out into the atmosphere. So the speed of light does change. It's fixed in a given material. Okay, so that's just kind of a review of what we've done so far. So how does reflection work, and how do we predict what's going on? It's pretty simple. So you have some kind of surface. So this is your surface. And it's going to be, we're going to say it's reflective. We kind of know what that is, like a mirror. Because, I mean, even light reflects off of the paper. The problem with light reflecting off of paper is it doesn't come in like this. It's like if you had your pool ball, instead of staying, it would be a pool ball made of a lot of other little balls, and you hit the surface and it kind of explodes. That would be what you would see in this case. It goes, because of the surface is not completely smooth, the light ray comes in, and instead of bouncing off at one fixed angle, it bounces off in all directions, which is called diffuse reflection. But the one we're most interested in is reflective surfaces like mirrors. And what happens is you have a ray of light coming in, so here's our ray, and it hits the surface and it bounces off. So we call this, not indecent, but incident. Incident and light. That doesn't look right, but did I spell that right? Incident. I don't know if it's SCI or DCE. We'll find out in a minute. And this would be the reflected light. And when you measure angles, you could say, do I measure the angle from here, the surface, to the light, or do I measure it from the ray to the normal to the surface? And the answer is we do it to the normal. So if you draw a line here, and this line is perpendicular to the surface, then this angle, we'll call that theta sub I, and the angle from the normal, so this is our normal line, we'll call this theta sub R. So theta sub I is called the incident angle, and theta sub R is the reflected angle. And the law of reflection says theta sub I equals theta sub R. So, and that's what you would expect. I mean, the lower, the greater this angle, or the lower that angle, the lower the angle that it bounces back up at. So you see that if you look at a smooth lake, and you can see the reflection of whatever's behind it, the mountain, if you want a nice picture. Or if you're using it to, if you have a plane mirror, if I look here, so what's happening is the light that's coming in this angle will bounce off at the same symmetric angle and go to my eyeball. So if I look at a mirror here, I'm going to see I'll probably see Elias. Okay. If I stand here, I'm going to see myself. There, I'll probably see Michaela or somebody like that. Maybe not. Maybe there. Okay. So that's not rocket science, right? That's what you would expect. Now, specular reflection, that is what I was just talking about. So let me just describe what that is. So if you have a surface, but it's a rough surface, so I'm going to make it a little rough surface here. So if the light ray comes in and it hits the surface, instead of bouncing off all in one direction, if it goes off in lots of different directions, like that. So that's what specular reflection is. Like I said, that's a paper. You can't see your image in a paper, reflected image. Actually, I might have got those mixed up. Because diffuse sounds like more like the right answer. Okay, let's do that. So yeah, made a mistake. I know, it's amazing, but it does happen. Okay, this is diffuse, sorry. Specular is what we think of as normal reflection. So let's correct myself. Okay. Like I said, we're going to be dealing with this kind of reflection, not that reflection, because there's not much to say about that. Okay, we already talked about the law of reflection. Okay, so that's it for we've done half of the chapter already. Now, refraction is a little more complicated. So refraction is associated with where you go from one medium, like a vacuum or air, to another medium that's transparent, like glass, different kinds of glass. And instead of bouncing off, the light ray is transmitted, but it doesn't go straight through. So here's the interface between the two materials. So let's say this is air and this is glass. And if we did an experiment, and we'll be able to, when we go back to on Monday, we'll we'll demonstrate some of this stuff instead of me just drawing pictures. So if, say you have a light ray coming in, so again we're using ray optics. The light ray comes in, it doesn't go straight through. It doesn't go just like that. It bends, the light bends. So you still have an incident ray, and in this case you have a refracted ray, and the angles are measured relative to the normal. So again, I'm going to draw a line here that is perpendicular to the surface, and I'm going to make it longer this way. So, okay, so again, defining the angles, this angle between the light ray and the normal, that's called theta sub I, and the angle between the normal, the other direction, is theta sub R, but they have different meanings now. Well, the first one's the same. That's angle of incidence. I think it might be that. Incidence. Yeah, angle of incident or angle of instance. Anyway. And this is the angle of refraction. These are in degrees, not radians. Now the question is, how do we calculate what the angle of refraction is based on the angle of incidence? So this guy named Snell did some observations and he came up with a result. But before we can do that, we have to define something which is called the index of refraction. So we're going to use the letter N to represent why we use N for index of refraction. I don't know, but that's, I guess we ran out of letters. So the index of refraction is the speed of light in a vacuum, which is the maximum that it can obtain, divided by the speed of light in a substance. And I said that the speed of light in anything other than a vacuum is less than the speed of light in a vacuum. So what we can say is that N is always less than or equal to 1. In a vacuum, it's equal to 1. Okay, so this is bothering me that I don't know how to spell incidence, so I'm going to look it up. Let's see, incidence. Angle of refraction. Oh, I guess I have to look up angle of incidence. It's with an I. So it's INCIDENCE. So I did get it right this last time. So what did I? So it's the incident angle or the angle of incidence. Now, just to give you an idea of what kind of, for glass, just normal glass. Well, I'll look it up in the book here. So I'm going to look up under index of refraction. 1081. Okay, so it says glass, there's crown glass, light flint glass, blah, blah, blah. It's about 1.5. So the index of refraction of glass is about 1.5. For water, I think it's about 1.3. Let me look here. For water, it's 1.333. I don't know if there's any significance to that, but it's 1.333. Diamonds, N is equal to, should bring my book over here. I'm getting instead of walking. Did I say that? Okay, I was wrong. It's greater than or equal to 1. Diamonds, 2.4. Okay, let me fix that. Okay, fix that. The other way around. Pesky details, right? So it's greater than 1. So what that means is that you could then calculate what the speed of light in glass is. It's going to be 3 divided by 1.5, which is going to be 2. So it'll be 2 times 10 to the 8. And notice the high index of refraction of diamonds. So that's the property of diamonds that make them do what they do, which is reflect light, or refract light, really, refract light, and we'll talk about that some other time. So now that I have defined the angle of incidence and the angle of reflection, and I've defined what the index of refraction is, so if we know, in this case, looking at our example, the index of refraction of air is pretty close to 1. It's 1.000 or something, so we're going to just use 1. And the index of reflection of glass is 1.5. So the result is called Snell's law. It says that N1 times the sine of theta 1 is equal to N2 times the sine of theta 2. You could also say it's the N1 times sine of theta incidence, in our case here, N2 times the sine of theta reflection. So if we know the angle of incidence and we know the two materials, we can calculate the angle of reflection. So let's just do a problem. Let's say theta incidence is 30 degrees, N1 is 1, and N2 is equal to 1.5. What is the angle of refraction? And it should be less because I told you it's supposed to do that, so it doesn't work out that way. So you'll do 1.0 times the sine of 30 degrees is equal to 1.5 times the sine of the one we're trying to find, the angle of refraction. So we get that the sine of the angle of refraction is equal to 1 times the sine of 30 degrees divided by 1.5. So let's see what we get. So the sine, let's change my calculator to degrees. One of the few times we do that in physics. So we're going to change that to, oh, it is already in degrees. Good. Mine's already in degrees. So we take 1 times the sine of 30 divided by 1.5. And we get that the sine of the angle of refraction is equal to 0.333. The sine of 30 degrees is a half. So then you take the inverse sine. So the angle of refraction is the inverse sine of 0.333. So inverse sine of the answer. And you get 19.5 degrees. Okay. If you had diamond, it would be refracted more. If you had water, it would be refracted less. And what happens with with your glasses is because of the curvature, it's due to the curvature of the glasses, whether it's bent out or bent in and how much between the two sides of the glasses, and also what the glasses are made out of. So what happens with the lens, and we'll talk more about this in the we'll talk about more of this in the next chapter, but because we're not going to talk about lenses yet, but I just want to give you an idea of what happens. So let me draw a lens for you. So here's a lens. And so what will happen is the light ray will come in to the lens and it'll be bent towards the center. And if you have a light ray coming into this part of the light, then it'll be bent towards the center. And these two lines will intersect at some point. That's called the focal point. And we're going to stop now because I said I was going to stop early so I can go to this interview. So we'll see you on Monday. Enjoy the rest of your day on vacation.